Okay, so we're progressing through our unit on sound and waves. And here, in lesson number 4, we're going to talk about sound intensity, which many people would identify as, how loud a sound is. When a sound is released from a source, okay, so here's some speakers at an outdoor concert. It basically forms a growing sphere of waves around the source that moves out and gets farther and farther and farther away from the source. Now, here in this diagram, these are drawn as concentric circles, but really, if you can visualize, they're almost concentric spheres of sound, compressions and rarefactions in the air. And as, of course, you get farther and farther and farther, the intensity of that sound decreases. It decreases for a few reasons. The intensity of a sound wave, then, is defined as the rate of power that passes through a surface area A that's perpendicular to the wave's direction. So the intensity is equal to the power of the sound wave divided by the area contained within this area A. So if the source creates a sphere of sound, then this area is basically the surface area of a sphere. So the intensity of the sound wave is equal to the power of the sound wave divided by the intensity of, the area of the sphere. And of course, because this is a growing sphere, because the sound wave moves outwards and the sphere gets larger and larger, you can see that the intensity is a factor of 1 over r squared. And so it dies off as a 1 over r squared. And so basically, we could write this without knowing the power and without concerning ourselves with 4 pi. We could write that the intensity of the sound at point 1 over the intensity of sound at point 2 is simply equal to a ratio of the distance that you are away. So this is mainly going to be the equation that we're going to use. So let's take a look at how we might use that in an example. So in an air show, a helicopter hovers overhead, and it causes sound waves to emanate uniformly. If one listener is 700 meters away and the other is 1,000 meters away, find the difference in sound intensity that's experienced by those two listeners. And so we'd say, okay, well, we know R1 and we know R2, 700 and 1,000 respectively. And so we can find this ratio, which is going to be able to give us the difference that's experienced by listener 1 at position 1 and listener 2 at position 2. And we can make our substitution, and we can solve. Basically what this tells us is that the sound intensity at 700 meters is almost twice the sound intensity at 1,000 meters. And it's because of this factor of r squared that even though the distance isn't half as far or half as close, the intensity is twice as much. The decibel system is basically used, it's a logarithmic scale, it's a logarithmic system, and what it tries to do is it tries to say, hey, these intensities, because of humans' extremely large range of hearing, the intensity system, or this logarithmic system, the decibel scale, attempts to kind of bring these intensities into a range where we can use basically a single number to reflect how intense a sound is. So it's simply a different representation of these intensities that we've been talking about. Intensities is, of course, if you look at the units for intensity, power, which is in watts, over area, which would be in meters squared. Intensity is basically in watts per meter squared. The decibel is basically a unit that reflects that, but we create this new unit, right? The new unit is a decibel, and it basically represents the log of this ratio. Okay, so in most cases where we're going to do examples, I naught, which is the initial sound intensity, it is considered a constant, and we compare it to basically the threshold of hearing, which has a value of 1.0 times 10 to the minus 12 watts per meter squared. So a normal conversation involves sound intensities of about 3.0 times 10 to the minus 6 watts per meter squared. What's the decibel level for normal conversation? And so here's the two sound intensities that we'll use. I is 3.0 times 10 to the minus 6. I naught is 1.0 times 10 to the minus 12. Again, this is a constant, the threshold of hearing. And we can say that beta, the decibel level, is equal to 10 times the log of this ratio. And when we actually put these numbers in, we get a value of 64.77 decibels. And so basically the sound level is about 65 decibels. So normal conversations are around this level. And so that gives you a pretty good comparison point. How loud in decibels would the sound for a rock concert with music intensity 2.0 watts per meter squared? That is a huge intensity at 1.0 meters, which is very close. How loud in decibels would that sound be if the person's 100 meters away from the source? Okay, so what we need to say is, well, we know what I1 is, we know R1, and we know R2, because this intensity I1 happens at 1.0 meters. R2 is, of course, 100 meters away. So this is a two-step problem. First, we'll find the sound intensity in watts per meter squared at the new location. And when we make this, when we cross multiply and when we solve this, we find that I2 is about 2 times 10 to the minus 4 watts per meter squared. And now we'll use this to calculate the sound level in decibels at this new distance, which is about 83 decibels. So at 100 meters away, we get a sound level of about 83 decibels. It would be interesting for you, in fact, to calculate what the sound level would be at 1 meter away in decibels, and then you could compare that decibel reading to this decibel reading. That's left as an exercise for the student.